You know, I really should have queued up some intro music for this one, and I did not. So shame on me. Anybody has any ideas? I'm all ears. Let me know. But anyway, moving right along. Give people just a couple more moments here to hop on in. Let me go ahead and pop this over so y'all can see me. Hello, my name's Rob. I work at Bridgepoint Technologies, and this is episode 3 of our Lunch and Learns. Going to be focused primarily on F sharp for my next part of this series. It's going to span multiple episodes. Don't quite know how many episodes it's going to take yet. I haven't actually worked out how many episodes we'll need to get from start to finish. So, anyway, diving right into it, this is not a complicated game. It's pretty simple. I'm just using it more as a means of getting started with F sharp development from start to finish. What does a library look like? What does a program look like? What do unit tests look like? Just diving on into the whole thing from start to finish. So, with that said, let's go ahead and dive into what we're building real quick. I chose what to me is a Flash game that one of the many Flash games that you play, like a Newgrounds, Congregate, whatever, that have been used to be all the rage a decade ago, called Tepiku. It is a game intended for 3 people. The implementation I played was not multiplayer, it was always just you and 2 computer opponents, and it involved dice, the regular 6-sided dice that we're used to. I say non-traditional. We'll get into that a little bit later. It involved 6 dice, 3 people. That's basically it. That's the setup. Each player has dice. Dice is called a board, mostly for the purposes of referring to it pretty easily. Players bet to start a round. So essentially, they'll place a wager. I want to wager 1, 2, 4, whatever. And mathematically, we'll get into what rational wagers are and what rational wagers aren't later, but you want to start small. So whatever we build is going to have that kind of baked into it. And what happens is after everybody wagers for the first time, they roll their 6 dice. They basically define their board by rolling those dice and then scoring up the results. Out of the 3 people, whichever person has the lowest board, the lowest score for their board, is the fish. And whichever person has the highest score for their board is the hook. And it's called fish and hook for the obvious reasons. The fish is on the hook to pay whatever the amount that's been wagered is to the hook. And the fish can do something about this, though. It's not like you just roll and you're stuck. There's a room to improve your situation here. And how you do that is by choosing to re-roll some of your dice, or all of them. You can pick however many of the 6 dice you can have. You can re-roll as many as you want. There's a cost though, because then the pot doubles. The amount everybody's wagered, that amount doubles. So, say everybody wagered 3 and the initial round is 9. The price of re-rolling your dice is that 9 doubles to 18. And what happens after the re-roll is you figure out who the next fish is, and that person then has the same decision. Do they want to double from 18 to 36 and re-roll, or they want to just go ahead and pay that 18 to whoever's in the hook? And this process basically repeats until either somebody chooses to pay and then they lose however many whatevers you're using to keep track of who's winning and who's losing, or the pot becomes so large that whoever is the fish is basically bankrupted by this process and they end up running out, and that's it. Game is over when somebody runs out of whatever it is you're keeping track of things. And I mentioned that the scoring is a little non-traditional. So rather than just having the normal dice, 1, 2, 3, 4, 5, 6, there are different icons that have different values on the dice. So you've got skull, ingot, gem, fire, water, and person. And they each have different point values. Skulls are worth -2 points, ingots are worth 1 point, gems are worth 2 points, fire is 3 points, water is 4 points, and a person is 1 point. Now, there's a little bit of some meta rules going on here in that some of these dice, their point values are dependent on other dice. And you'll have to forgive me because I just realized I forgot to fix a bug in the slides. Yay me. So this sort of meta scoring is fire and water cancel each other out. So if you have fire and water, their point values both turn into 0. People are a little different in that each individual person is worth the sum total of the number of people on your board. So let's say you get what's actually a fairly lucky roll and you've got 5 people out of your 6 dice. Each individual person is worth 5 points, and the 5 people on your board now total 25 points. So let's just go ahead and walk through an example round to kind of give you an idea how this works. We've got 3 players, Byron, Bruno, and Bob. Byron, Bruno each wager 1. Bob's feeling a little lucky, he wagers 2. So our initial pot is for whatevers. It doesn't really matter what unit we're using because it's all going to be relative to the game, and everybody starts off with the same amount for fairness reasons. So now that we've got our pot established, everybody goes ahead, rolls their 6 dice. Byron gets 3 skulls, 2 gems, and a fire. Bruno gets a skull, ingot, 3 gems, and a person. Bob gets gem, not a gem, an ingot, fire, water, and 3 people. This ends up getting scored as follows. 3 skulls, that's -6. 2 gems, that's +4. That leaves us with -2. When you sum them together, fire's worth 3, so Byron ends up getting 1 point. Bruno, 1 skull, an ingot, that's -1. 3 gems, that's a +6. +6, -1, that gives you 5. He only has 1 person, so that person's worth 1 point. 5 plus 1 gives Bruno 6 points. Bob's got an ingot, fire and water, so that's 1 plus the fire and water cancel each other out 0, so we're still at 1. But 3 people, so each person's worth 3. That's a total of 9. 9 plus 1 gives Bob 10 points. And now we go and figure out who's the hook and who's the fish. Byron has the least amount of points, which makes him the fish. Bob has the highest number of points, which makes him the hook. And this is where Bob has a decision to make. Not Bob, Byron, excuse me. Byron has a decision to make. Do I just pay Bob 4, or do I do something about my situation? Half of Byron's board is skulls. It would be very difficult for Byron to grab those 3 dice, roll them again, and not improve his situation somehow. So Byron chooses to do that because 4 is not a big payout. Byron goes ahead, re-rolls those 3 dice, scoring his new hand. He gets another skull, but the other 2 skulls have turned into people. So now he's got skull is -2. He's got 2 gems. That's +4. So now we're up to +2. Fire is 3. Now we're up to 7. 2 people. Wait, did I score this wrong? 2, 3, 5. No, I spoke it wrong. So Byron ends up getting 5 points now, but the pot has subsequently doubled to 8. And because Byron has 9 points and no one else re-rolled any dice, so their boards stay the same, Byron is no longer the fish. Bruno is. And Bruno has the same decision to make. Do I try and re-roll to improve my lot, or do I just pay the 8 points? So Bruno decides, yeah, I'll take my skull and my ingot and re-roll them to see what happens. Well, Bruno's luck isn't so good. He rolls again. His skull doesn't change, it's still a skull, but he ends up getting another skull. So he's actually made his situation worse. His new board score is only 3 points. He's still the fish, but now the pot is worth 16 instead of 8. At this point, Bruno decides to cut his losses and move on. He just pays the 16 out to Bob, and we're done. This situation repeats until somebody runs out of whatever it is we're using to keep track of what's going on. So far, so good. That's pretty much the whole game. So I think at this point in time, let's go ahead and switch over to Visual Studio and sort of walk through what's going on real quick. I have a solution open here. It's got 3 projects, a console project that we are not going to mess with much today. I don't think we'll have time to get to it. A core project, which is this is going to be our business logic, the equivalent of our business logic DLL. This is going to be where we put the functions that run the game and manage the game in. And then, like any good developer, we have unit tests. So I have a unit test project that I have gone ahead and stood up some unit tests for. Because, we do test driven development. So you write some unit tests first, and then you write the code to make sure the tests are good. So here we have a definition of 3 boards, some testing to make sure that a function that determines if a particular dice exists in a board works, and then a second set to test whether the function that counts how many of a certain dice exist works, and then a third one to sort of test whether our ability to score the boards to sum up their value works correctly. So now that we've got some baseline tests put in place, let's go ahead and start building the game. Sells one nice, lovely, empty game module. Like all good programs, you start with the smallest blocks and work your way up. So let's define the face of our dice. Ingot, gem, fire, fire, person, skull. These are the 6 different types of the 6 different face on the dice we have. In F-sharp terminology, I've essentially created a union type. So a dice face, it's kind of like an enumeration in that a dice face only ever has one of these 6 values. There's no way I can define something else for the dice face. I think the key distinction to make between an enumeration and this union type here is that it's sort of implicit in other languages like C sharp and other languages that support enumerations, in that these enumerations can be translated into numeric values. Like there would be an assumption baked in that ingot equals 0, gem equals 1, fire equals 2, so on and so forth. Some languages even allowing you to specify these values. For our purposes, and because of C sharp, not C sharp, F sharp, a union is different in that there's no numeric conversion. You're never, without writing a separate function that links the two together, you're not going to be able to go from ingot to 0 or 1, depending on how you like to count. So now that we've got this initial building block, the next thing we need to do is define what it is to be a board so that we can start doing our operations to make the game work. So a board is essentially a list of dice, our dice being represented by the type dice face. And we'll get into a little bit of the why later, but one of the things that you'll note about F sharp is sometimes the order of parameters and the notation within the language seems backwards, which is why I'm declaring a dice face list instead of, say, a list of dice face. Now that we've got our 2 types out of the way, we can actually start building the functions that we need to figure out to basically score a board. So the first thing we need to do is determine whether the board has a particular dice, like a particular die value. So let's see, let has face board. So we're going to write a function called has that accepts two parameters, face and board. And what we want to do here is, does whatever value we specify for face exist on the board? That's the question we need to answer. So we know that board is a list and that we're passing in a dice face. So based on these assumptions, there are a lot of built-in functions in F# to operate on lists. It's a lot like the functions that you get in, for those who write C#, a lot of the things you see here have link equivalents for the lists over there in that world. So list.exists is what we're going to start with. And just like in link, we need to define a function that specifies what we're looking for. So function that accepts a dice face, and let's see if f equals the face that we've been passed into this function. That's what we're looking for. So there's our test. And then we tell it to operate on the board. And that's it. We now have a function that can tell us whether a particular face exists within a board. And likewise, we will need a function that can tell us how many of a certain face exists in the board. We'll build a similar function called count, because we're mundane like that. Follow the same parameter list, face and board. We will use a different list function. This one's called fold. And what it essentially does is it has an accumulator that is kept in memory from one iteration to the next. Fold is going to operate on every element in the list. It's going to operate on everything in there, running a specified function. And the output from that function is added to the accumulator. So say, for example, if I had a list that contained the number 1 8 times, and a function that said, take my item to the list and add it to the accumulator, then and say that the accumulator starts at 0, it goes 0 plus 1 is 1. My accumulator is 1 now, so 1 plus 1 is 2, because I just went over the next item in the list. Go on to the third item, it would be 2 plus 1, because my accumulator is now 2. The third element's still a 1, so 2 plus 1, so on and so forth. And at the end of the day, the value in the accumulator would be 8. And I've just developed a function that summed all the numbers together. In this case, we're just trying to count how many of a certain face is there. So rather than summing, we only want to return a value if it's there. So let's go ahead and define our function again, our accumulator, and then our dice face. Start by taking our accumulator from the previous runs and adding to it a small if statement. So if, and the same test. If our current element matches the dice face that we've been passed, then we want to return a 1 because we want to add 1 to the accumulator because we found it. Otherwise, specify 0. And then following the convention, we have to now define the initial state of our accumulator. Well, before we start looking at dice, there are no dice, so we set that to 0 and then operate on the board. That's it. This will give us a function that will count how many of a particular dice face exists within a board. These will become the two building blocks that we need in order to determine the score of a board for basically summing up the score of the individual dice values. So the next function we're going to put together actually scores one dice from a board. Call it die value, pass in a die and a board. And if you're wondering why we need to know the whole board when we're just scoring the individual dice, that's where the meta rules come into play. If fire is canceled by water, the score of an individual person's determined by the total number of people. And we need to account for that in this function. So we can't just look at the particular die we have to look at the whole board as well. And this is the point where F sharp's match statement really comes into play. So what we're going to do is we're going to match the specified die with all the potential options. Let's start with a skull, because that one's easy. Skulls are -2 points. It helps if I can type. Ingots are 1 point. Gems are 2 points. Fire. Well, fires are 3 points unless there's water. Then there's 0 points because fire and water cancel each other out. So we need to add a small if test. It's going to follow the same format as the if test we wrote in count. So if as water board, then the value of fire is 0, else it is 3. And likewise with water, if there's fire, then water is worth 0 points, else it is worth 4 points. And you'll notice that even though this is syntactically correct and the system seems mostly happy with it, it's complaining about die. And it's telling me that because it's an incomplete pattern match. I'm missing something. In this case, I'm missing person because I haven't added a condition for that yet. And to me, that's actually one of the nice things about it. I know I alluded to this in an earlier lunch and learn, but this is an example of that. The environment is helping me remember to be a better developer. So let's go ahead and implement person. Person's a little different. We don't need to know if there are other people. We need to know how many other people there are. So the score for a person is the count of the total number of people on the board. And that's it. We now have 3 functions that tell us whether a board has a particular dice, how many of that dice there are, and then it'll allow us to score each of the dice for a particular board. So now we just need to put this all together in order to figure out what the score is for an entire board. To do that, let's build a summing function. And again, very boring names. Let's sum a board. We can reuse the same pattern we have for the count. It's just instead of passing in a 1 or 0 to the accumulator, we'll just pass in the value for each dice. So list.fold, and then our accumulator function becomes accumulator die value of whatever our particular die face is and the board itself. And then no need to pass anything other than 0 as our accumulator because when you score something, you always start in the beginning. This is going to operate on our board. That should do it. Save it. Build it. Life is good. And if my own notes on this subject are correct, now I've developed everything we need to make sure our unit tests pass. Let's go ahead and switch back to our unit tests real quick and check them out. Got 3 boards defined. One that only has 2 fire and a water. Second one, let's see, we have 2 skulls, 2 gems, and a person. And a third one with 3 people and 2 gems. We have 2 sets of board has tests here to test the has function to make sure that it's correctly determining whether a particular dice exists in a board. And likewise, we have assertions to make sure that the count function is correctly counting the number of dice within the boards. And then finally, a function to test sum, which tests the total amount of the boards. And you'll notice that there aren't any specific tests for die value here. You could put them in, you could not. That really depends on how much unit testing you want to do, because the die value function is required for the sum function. So die value is implicitly tested by making sure sum is doing what you want it to do. So let's go back and do the math real quick. Board 1, fire, fire, water. Fire cancels out water, water cancels out fire. The total point value here is 0. Board number 2, got a skull, -2. Another skull, -4. Pair of gems, that's +4. Those two cancel each other out. And then we have one person. So the board number 2 score should be 1. Board number 3, we have 3 people and 2 gems. So the gems are 2 each, so that's 4. Each person is worth 3 because there are 3 people, so 3 times 3 is 9. 9 and 4 is 13. So there we have it. When we check our unit test here, 0, 1, 13, they are the values that we expect. I should be able to fire up these unit tests, all pass. And they do, as expected. So far, so good. So I know I only booked half an hour and everybody is busy. So I think we can make a little bit more progress today and use that to sort of cover a little bit more about things in F sharp. So let's go ahead and define a player, someone who participates in the game. And currently, all they need to have is a board. Actually, let's clean that up a little bit. And a name, so we know who the player is. And you will notice that this is the first time in the application that I am specifying the types of objects within something else. Like the sum function die value count has, I'd specified no types anywhere within them, and the system still understands what's going on. This is due to the type inference of F sharp. It's basically working backwards from the code to figure out the types of things. So take die value, for example. It has determined that the type for die is a dice face because in the match function, I refer to the values that make up the dice face union. It's also determined that board is a list of dice face because it's worked backwards from the fact that I refer to board in the has and count functions. And subsequently, when it looks at the has and count functions, it realizes that I am calling the list functions on the board and that the individual accumulator functions that work with the list are of type face. And it puts all this together and determines that each face is an individual dice face. The dice essentially also a dice face, and the board is a list of dice face. Going back here and adding a little bit more code to the system, now that we can define a player, we have everything we need in order to take a look at a set of boards, a list of boards, and figure out who the fish is. So let's go ahead and write a quick fish and hook function. That fish player equals, and I'm going to switch up the notation a little bit here for educational purposes. Players, not list, let. It helps if I use the right word. And we're going to use a different list function this time, list min by, because we want to find the minimum value. We want to find the lowest scoring board. We want to find the minimum value of all the boards in our list of players. So min by follows the same convention as the other ones. So we define a function that returns the value of the board so that min by can then tell us which board scores the least. So we will sum the board for every object that's passed in. Also helps if I get my naming consistent. And you'll notice that Visual Studio is happy and this code looks fine, even though I haven't passed in a second parameter to min by. Like above where we've got fold or exists, we always have to tell it to work on the board. This code is functionally the same. The difference is we're specifying players essentially as a start point, and then through use of this piping operator, passing it into list.minby. And the reason why this is useful, and this ties into the reason why a lot of times the convention in F sharp is to do your function parameters where that the thing you're operating on is the last parameter in the list, is to allow for this kind of notation. Because in the great many instances and programs, we're only ever, whatever function we're developing is only ever really operating on one thing. It's just doing things to it. So this notation would allow us to easily start with players, do a min by, and then, or form some operation and then easily move on and do something else. Follow it up with a third thing, and then finally, the last thing that gets returned is the result of the function. And syntactically speaking, this makes it pretty obvious that we're operating on players and we're doing this list of things to it. So if we wanted to implement the hook function in the same way, however, just using the other notation, then we would merely start by declaring the max by function and pass in board. Players, not board, because I need to stick with the variable declarations as I write them. Yeah, I have burned through my half hour and some change. So this is a good place for actually us to stop for today. If no one has any questions, I would like to thank everybody for watching, and I will hope to catch you guys here in a little bit. I'm going to try and get us on a week-to-week schedule. I imagine I'll be back in 2 weeks doing this, and I am working on a different presentation for on an entirely different subject for us to put together for next week. So we'll start to increase the velocity and the content and make sure we all stay on each other's toes regarding everything that's going on. So, point, I would like to once again thank everybody for watching and so on and so forth. And I'll let everybody get on with their days and catch you later.